Hey everybody, it's Mike from A3Academy, and today's video will be on Coulomb's law. So let's jump right in. Okay, here we have two charges labeled Q1 and Q2, and these are point charges, which basically means that their spatial size is negligible relative to the other distances we're going to be talking about. So they have different charges, and the distance between them is r. So what we're interested in is the force between these two charges. And that is given by this equation here called Coulomb's law. And it states that the force is equal to K times Q1 times Q2 over R squared. And K is a proportionality constant equal to 8.988 times 10 to the 9 Newton meters squared per Coulomb squared. Another way we can write this equation is in terms of epsilon 0, or the permittivity of free space. And you might not come across this that often, but it's still useful to know. And epsilon 0 is 8.85 times 10 to the minus 12 Coulomb squared per Newton meters squared. Okay, let's look at an example. What is the electric force on an electron of a hydrogen atom due to the single proton in its nucleus? Okay, well, we have a diagram. Q1 is our proton, it's positive. Q2 is our electron, it's negative. So we're interested in F21, which is the force exerted on Q2 by Q1. And the way we find this is by using our equation. But we need to know a couple of values here, mainly r, which is the distance between the proton and the electron, which is given as 5.3 times 10 to the minus 11 meters, and e, which is the charge on each of these. Now, e is actually an elementary charge, or 1.6 times 10 to the minus 19th coulombs. But it will be negative for the electron and positive for the proton. But when we calculate the force, we're only interested in the magnitude. So we plug that into our equation, and we get that the force is equal to 8.2 times 10 to the minus 8 newtons. Now, F21 is the force exerted on 2 by 1. But we also have F of 1, 2, which is the force exerted on Q1 by Q2. And these are equal in magnitude, but they are actually opposite in direction. Remember that we have a positive and a negative charge here, which means that the force is an attractive one. So both F12 and F21 will point toward each other. Okay, let's look at another example. We have a 6 millicoulomb charge placed at each corner of a square, and this square has a side length of 0.1 meters. And we're interested in finding the magnitude and force on each charge. So we have a diagram here. This is our square, and we labeled the four corners Q1 to Q4. And for simplicity, we're going to stick with the charge of each of them being Q, and the distance or the side length being D. And we'll just plug in the actual values at the very end. Since a square is symmetrical, we only have to look at one corner because the force on each of the four corners will be the same. But it's a little tricky because we have three forces acting on each charge because there's three other charges. And we can label these if we look at, let's say, Q2. We have F21, which is the force exerted by Q1, F23, which is the force exerted by Q3, and F24, which is the force exerted by Q4. And the way we'll get to our answer, which is the magnitude and direction of the resultant vector, is by adding the components of all three of these. Now, if you guys haven't already, go check out Wallace's video on vector addition because it will come in very handy, and this is a skill you need to know to do problems like this. So click on the annotation and watch that video, and then come back here when you're done. So let's calculate each one of these three vectors. Let's look at F21 first. So we have our equation here. We know that Q1 and Q2 are both just equal to Q, so that's why there's a Q squared on the top, and the distance between them is D. And now we will look at the components. So the x component is just the magnitude multiplied by the cosine of the angle, and the y component is the magnitude multiplied by the sine of the angle. But since f(1) is horizontal, the angle is just 0. And cosine of 0 is 1, and sine of 0 is 0. And from that we get that the x component is kq squared over d squared, and the y component is 0. Now let's do the same thing for f(3), which is the vertical one. The angle in this case will be 90 degrees, and cosine of 90 degrees is 0, and sine of 90 degrees is 1. So here we have the x component is 0, and the y component is kq squared over d squared. The last vector is the diagonal one, f(4), but remember that the distance here is actually not d, because the length of the diagonal of the square is √2 times d by the Pythagorean theorem. So when we calculate this vector, we actually have to use √2d as the distance, and that squared is 2d squared. Again, the same thing as before, except this time the angle is 45 degrees because it's diagonal, and cosine and sine of 45 degrees are √2 over 2, and when we substitute that in, we get each of these is equal to k times √2q squared over 4d squared. Okay, that wasn't that bad, but we're not done yet. We need to add the x components of each one of these and the y components to get f of 2x and f of 2y. Well, we have all those values. We can plug them in, and we get that both of these are equal, and they're equivalent to kq squared over d squared times 1 plus √2 over 4. Now we have the x and y components of our resultant vector, and to find the magnitude of the vector, we use the Pythagorean theorem. So f2 is equal to √f2x squared plus f2y squared, and again we just plug in the value above, and we get that f2 is equal to kq squared over d squared times √2 plus 1/2. This is the last step. All we do is plug in the values for k, q, and d, which are 8.988 times 10 to the 9th, 6 millicoulombs, or 6.0 times 10 to the minus 3 coulombs, and 0.1 meters. And when we substitute those into the equation, our final answer is 6.19 times 10 to the 7 newtons. The very last thing we have to find is the direction of this vector, because this is just the magnitude. And we use a handy trick from trigonometry, which is that theta, or the angle, is the tan inverse of the y component over the x component. But remember that the y and x components were equal, so their quotient is 1, and tan inverse of 1 is 45 degrees, so that is the direction of the resultant, 45 degrees above the x-axis. That was a pretty tricky problem, but if you work your way through it, and especially if you draw a diagram to help you, it becomes a lot simpler. There's a lot of steps, but they're all relatively easy to understand. Alright, that's it for Coulomb's law. I'm Mike from A3 Academy, and as always, the more you know, the better you are.